Hello everyone and welcome to the third video lesson for Chapter 8 of the Foundations of Scalable Systems. In the previous lesson I delved into some of the details of Google App Engine, the serverless platform of the Google Cloud, and showed how it works and how it can be tuned to balance performance and cost. And in this lesson I'm going to contrast the features of Google App Engine with AWS's Lambda platform. So let's dive in. Lambda is Amazon's serverless platform. The underlying design principles and major features echo that of the Google App Engine serverless platform and other serverless platforms too. There's an awful lot of commonality. Developers with Lambda upload code which is deployed as a service known as a Lambda function. When invoked, Lambda supplies a language-specific execution environment to run the function code that you've uploaded. Here's a very simple example of a Python Lambda function. The function simply extracts a message from the input event and returns it unaltered as part of a HTTP 200 response. In general, you implement a function that takes an event and a context parameter. The event is a JSON formatted document encapsulating data for a Lambda function to process. For example, if the Lambda function handles HTTP requests, the event will contain HTTP headers and the request body. The context contains metadata about the function and its runtime environment, such as the function version number and the available memory that's for the function to execute in its execution environment. Lambda functions can be invoked by external clients over HTTP. They can also be tightly integrated with other AWS cloud services. For example, this enables Lambda functions to be dynamically triggered when new data is written to an AWS S3 storage service, or monitoring events is written to an AWS CloudWatch service. You can also integrate tightly with the AWS SQS messaging system. If your application is deeply embedded in the AWS infrastructure, Lambda functions can be of great utility in designing and deploying your architecture. So, given the similarities between serverless processors, in this section I'll just focus on differentiating the features of Lambda from GAE in terms of its scalability and its cost. So first let's look at the Lambda function lifecycle for processing a request. When a request first arrives for the API defined by your Lambda function, Lambda downloads the code for the function, initializes a runtime environment and any instance-specific initialization, for example creating a database connection, and it finally invokes the code handler for your function. This initial invocation is known as a cold start, and the time taken is dependent on the language environment selected, the size of the function code, and the time taken to initialize the function. Like in Google App Engine, lightweight languages such as Node.js and Go will typically take a few hundred milliseconds to initialize, whereas Java or .NET are heavier weight and can take a second or more. Cold start costs can be mitigated by using provisioned concurrency. This tells Lambda to keep a minimum number of runtime instances resident and ready to process requests with no cold start overheads. The no free lunch principle applies, of course, and charges increase based on the number of provisioned instances. Once an API execution is complete, Lambda can use the deployed function runtime environment for subsequent requests for the same function. This means cold start costs are not incurred. However, if a burst of requests arrives simultaneously, multiple runtime instances will be initialized, one for each request. A key difference with Lambda is that, unlike Google App Engine, Lambda does not send multiple concurrent requests to the same runtime instance. This means all subsequent simultaneous requests will incur additional response times due to cold start costs. When you define a Lambda function, you specify the amount of memory that should be allocated to its runtime environment. Unlike with Google App Engine, you don't specify the number of virtual CPUs to utilize. Rather, the computational power is allocated in proportion to the memory specified, and the memory sizes vary between 128 megabytes and 10 gigabytes per function. You choose this when you deploy a function. Lambda functions are charged for each millisecond of execution. The cost per millisecond grows with the amount of memory allocated to the runtime environment. So you choose more memory, you pay more. So for example, at the time of writing, the cost per millisecond for a 2 GB instance are basically twice that of a 1 GB instance. Lambda doesn't specify exactly how much more compute capacity this additional memory buys your function. Still, the larger the amount of memory allocated, then the faster your Lambda function will likely execute. This situation creates subtle trade-offs between performance and costs. Let's examine a simple scenario based on the costs for 1 GB and 2 GB instances and assume that 1 millisecond of execution on a 1 GB instance incurs 1 mythical cost unit, and a millisecond on a 2 GB instance incurs 2 of these mythical cost units. With 1 GB of memory available for a function, I'll assume this function executes in 40 milliseconds, thus incurring 40 cost units. But with 2 GB of memory allocated to a function, and commensurately more CPU allocation, the same function actually just takes 10 milliseconds, meaning that you're parting with 20 cost units from your AWS wallet. Hence, the bills will be reduced by 50% because by allocating more memory, you've reduced the execution time 4 times. You're getting 4 times faster execution with more memory. So this kind of tuning can be unintuitive, but it can surely save money and pay dividends. Obviously, it's very dependent on the actual processing your Lambda function performs. Still, if your service is executed several billion times a month, this kind of non-intuitive tuning exercise may result in significant cost savings and greater scalability, an all-round win. Like GAE, Lambda also auto-scales our functions as load increases. As the number of concurrent requests for a function increases, Lambda deploys more runtime instances to scale the processing, as you can see on the slide here. If the request load continues to grow, Lambda reuses available instances and creates new instances as needed. Eventually, when the request load falls, Lambda scales down by stopping unused instances. That's a simple version of what's going on, but in reality it's a little bit more complicated. All Lambda functions have a built-in concurrency limit for request bursts. Interestingly, this default burst limit varies on the AWS region where the function is deployed. For example, in the US West, Oregon region, a function can scale up to 3,000 instances to handle a burst of requests, whereas in Europe, Frankfurt, the limit at the time of recording is 1,000 instances. During a request burst, the number of instances will grow rapidly up to this region-defined burst limit. After that, only 500 new instances can be deployed per minute, regardless of region. During this time, requests that cannot be satisfied by the available instances, i.e. there's not enough capacity loaded in the Lambda platform to handle these requests are throttled, and HTTP 429 is returned to clients who must retry the request. Eventually, as the burst diminishes, instances are removed from the platform until a steady state of traffic resumes. So Lambda will scale up and scale down for you automatically. To complete this picture, you need to be aware that the burst concurrency limit actually applies to all the functions in the region associated with a single AWS account. So if you deploy 3 different Lambda functions in the same region under the same account, their collective number of deployed instances is controlled by the burst limit that determines the scaling behavior. This means if one function is suddenly and unexpectedly heavily loaded, it can consume the burst limit and negatively impact the availability of other functions that wish to scale at the same time. To address this potential conflict, you can fine-tune the concurrency levels associated with each Lambda function deployed under the same AWS account in the same region. This is known as a reserved concurrency. Each individual function can be associated with a value that is less than the burst limit. The value defines the maximum number of instances of that function that can be executed concurrently. Reserved concurrency has 2 implications. First, the Lambda function with reserved concurrency always has an execution capacity available exclusively for its own invocations. It cannot be unexpectedly starved by concurrent invocations of other functions. This essentially is what's known as a bulkhead pattern, as we'll see in the video lessons for the next chapter. The reserved capacity caps the maximum number of resident instances for that function. Requests that cannot be processed when the number of instances is at the reserved value will fail with a HTTP 429 error. And that's it for the major features of the AWS Lambda platform. Hopefully you can see that there are subtle differences between the way AWS Lambda and Google App Engine actually function at the detailed level. So in the next lesson, I'm going to take a case study based on Google App Engine to show an approach that you can utilize to balancing throughput and costs with serverless platforms. Thanks for watching.